Checking. Just sorry, I will start the session today on time. But I'll record and upload the session. Uh, if you are busy after 8, you can watch the video. And yeah, then we'll see the session. You can watch it on YouTube. I'll upload it today itself. Uh, okay. Okay. Good evening, everyone. So this is our second live problem solving session for the course Nanomaterial and Their Properties. This is just a second session, so I'll go over these slides one more time. We'll have 2 sessions every week. One on Saturday, first on Saturday, and then on Monday. We'll mostly discuss what was covered in the lectures that week and do some practice questions, which may be different for post TAs. And then we'll discuss the previous week's assignment for checking problem. So you don't necessarily have to attend both the sessions. You can attend any. Yeah. Yeah. My session is always on Mondays. Will be on 11th August. All right. So the links. There's a Excel sheet, I think, shared on the course website itself, where you can see the YouTube link for every week, the live session every week, the meeting link, and the Google Drive link is also there in the same Excel sheet if you don't want to copy this, but where the slides will be uploaded. So again, the lectures this week were also introductory. So historically, there have people unknowingly have been using nanomaterials. So, like on the left, you can see this cup. If you see it uh, normally lit from the outside, you see greenish color. But if you put the light inside the cup and or see it across, like so that the light comes through the cup, then you see a different kind, reddish color. That is due to gold nanoparticles inside the paint. Inside the paint. Similarly, in the paintings, ancient paintings, you will see different colors, like blue color, again, which is due to nanoparticles. You see the glass, how they stain the glasses in the churches. Again, they use different metal nanoparticles with distinct colors, add them to the glass, and it forms a nanocomposite. And here, depending on different sizes of the nanoparticle, you get different colors. So here, for example, of nanoparticle. So in the paint, you can see these distinct small particles in the high resolution transmission electron microscopy images. This is a single particle, again in nanometer range. which gives this distinct yellow color. And because this is made of nanoparticles, the color uh, doesn't degrade and is maintained over a much longer duration. So if you use organic dyes or organic compounds, they eventually over time deteriorate, lose the color. There are some self-assessment questions. How natural and man-made nanomaterial is obtained? Natural processes like geological processes like volcano, eruption of volcano, slow growth of crystals inside it's mental. They can give you material. Or biological methods, some bacteria and all produce particles. I think, or like the butterfly wings we covered in the last session. They have nanostructured wings, nanostructure in their wings. Like bottom up. So man-made, you have mainly two categories of nanomaterial: bottom up or top down. I'll go top down first. So top down, you have a large bulk sample and you go down, break it down to get nanoparticles. You keep on breaking it until it becomes fine powder, fine nanomaterials. Usually they do it with mechanical milling. And again, if you want to go to down to nanometer, they usually use wet ball milling because dry state, the temperature increases a lot, and then if the temperature is too high, those nanometer particles would agglomerate together to and form meso like micron size particles again. They won't go into nanometer scale. So you need liquid. So they are usually made in wet mills to lower the temperatures. Lithography is again just you use electron beam or light to remove material. Is there something like that to again get nanostructure? CVD, sol gel, these are all chemical methods. CVD is chemical vapor deposition. So you have species in gaseous state. It react on a substrate, giving you nanoparticles. Sol gel, I think will go over. Um, precipitation again, precipitation reaction. You have two salts which react with one another, and you get nanoscale precipitates. The challenging challenges for one big. There are a few significant challenges like safety. Nanoparticles, like metal nanoparticles especially, are really reactive. So they're very explosive actually. And there's also safety issues like our lung. If you breathe nanoparticles through your lungs, they get easily absorbed into your bloodstream, and again, that can have bad effects on your health. And even like get filtering it out of water or something like that. If you pollute groundwater with it, it's difficult to remove those particles. Imaging, again, it's very difficult since for bigger particles, you can use optical microscope, which is really readily available. You just need lenses, and for optical lenses, I would want the optical lenses to these small particles, but to see things in nano scale, you need to go down to nano scale. So if you know resolution is inversely proportional to the wavelength of the light, the resolution of the optical microscope. The wavelength is high. Okay. Yes. Wavelength high is higher for maybe radio. We give you larger resolution. I think it's proportional to wave. Proportional to wavelength. Yeah. So if you use smaller wavelength light, you can get much finer resolution. Okay, resolution. Yes. Resolution is the smallest distinct difference between two distinct points. So if you have two particles sitting at maybe 10 nanometers, if you see it on optical microscope, what we will see is just a single particle. You won't see the gap between these two. So to get higher resolution, you actually um, higher the resolution means the lower the nanometer. But yeah, the resolution is indeed proportional to length. Resolution, which was correct. Right. So smaller the resolution, uh, smaller the part, fine, better you can see. Uh, is inversely proportional to wavelength. So if you use visible light has around, I think, smallest wavelength is around 400, around 400 nanometers. To go below that, you use X-rays. X-ray may be smaller, maybe 100 nanometers, something like that. So for XRD, or if you want to see atomic spacing, you use X-rays. But I think yeah, you cannot use X-rays to see optical photos optically. To do that, we go to electron microscopy. So here you're limited by the wavelength of the light you can see through your eyes. Or for electron microscopy, uh, the energy of electron is again inversely proportional to the wavelength. So smaller wavelength, you get higher energy. So to give it higher energy, you just need higher and higher tension. So the energy would be just electron times the voltage, EV. So you go down to maybe kilovolts of energy, and you can impart voltage. And when you accelerate electron through those voltages, it gets a lot of kinetic energy. And if you remember the d Broglie wavelength, uh, it was lambda is equals to h upon lambda is equals to h upon p. P is a linear. And V, I think in terms of energy, you can say the root to lambda is equals to h over the root to E is your energy. So more energy you impart the electron, the smaller would be its wavelength. So smaller wavelengths you'll get higher resolution. So that's why we use electron microscopy. For uh, inorganic samples, you can use a very high energy electrons like 200 or 300 kV kilovolts of potential to accelerate the electron. We have kinetic energy. However, for if you use these high energy electrons for uh, biological samples, they damage the tissues and you won't get an image. So there actually they usually prefer 80 or maybe 120 PV systems, and they also cool down the sample itself. So the electron beam, when the electron hits the sample, it actually locally heats the sample too. That can also destroy the sample, so they cool it down, driving temperatures to prevent damage from the beam. The next challenge is just like this. How do you go down to nanometer scale? Yeah. And finally, even if you are able to produce small amount of nanoparticles in your lab, it's very difficult to scale them up to industry size, like produce large bulk quantity. Then we covered some different types of classes of nanomaterials. So first we have zero-dimensional nanomaterials. When all three measured dimensions are less than 100 nanometers, so all three dimensions are within the nanoscale. We call that zero-dimensional nanomaterial. Or you can say, in other words, no dimensions, 0D. So all, yeah, so zero dimensions are larger than 100 nanometers. The most common type of zero-dimensional nanomaterial is nanoparticle. And nanoparticles can be amorphous or crystalline. Amorphous nanoparticles, you won't have any regular arrangement of atoms. Like they can be single crystalline or polycrystalline. So if you go smaller and smaller, there's less chance getting a polycrystalline. Yeah, if you're 100 nanometers in that, you can. They can be either single or uh, and have multiple elements. They can exhibit different shapes, forms. They can be rod shaped or hexagonal plates or spherical, very large number. They can even be irregular shape. They can be exist independently or they can break. They can be anything. Like ceramic or picture. Right hand side, you have some ceramic, zirconium oxide, zirconia, all nanoparticles. Here you have iron nanoparticles, maybe 20, 30 nanometers. amorphous particles. Next, you have one-dimensional nanoparticles. So your one dimension is more than 1 nanometer, and the other two are less than 100 nanometer. So there you get one-dimensional nanomaterial. So they usually have rod long shape. The rod shape is the most on the particles, but they can be flat ribbons or um, hollow tubes, which are nanotubes, flat ribbons. Cross section can be hexagonal, circular, or rectangular. Uh, so only having one dimensional outside the nanoscale, another two within the nanoscale, you usually get needle-shaped nanoparticles. They include nanotubes, nanorods, and nanowires. Usually rods, which is straight, you call it. So specific shape. Nanowires used to be thinner, you can be curly or something like that. 1D nanomaterials, again, they can be amorphous or crystalline. They can again have single crystals or be polycrystalline, chemically pure and impure. Can be standalone material or embedded inside another material. You see your carbon fiber, all the things made of carbon fiber, those fibers can be again in the range, and you have some epoxy matrix. Because when those carbon fibers are embedded, like this, and they can be metallic, ceramic, or polymetallic. So next we have some 2D nanomaterials. Here, your two dimensions are not confined to nanoscale, but your third dimension thickness, usually thickness, lies in nanometer scale. So they exhibit a plate-like shape. If you've seen any plate in your home, big things, but the thickness is relatively compared to the diameter, it's very small. Plate-like shape. Two-dimensional nanometers, usually the example of these are nanofilms, nanolayers, nanocoatings. Nanofilms are usually just single, very thin single layer of material. If you have multiple of these, you can have nanolayers, or if it's on another material, coating another material, you can call it nanocoating. There you have some examples: gold nanoplatelets, yeah, triangular shapes or hexagonal, multiple shapes. Hexagonal copper iron oxide platelets. Again, they can be, you can follow all of these points, which are again similar to what the other two type of nanomaterials have. It's like amorphous, different chemical compositions. They can be single layer or multi-layer. So yeah, this 1D, it's usually very rare to find like half a rod of made of one material and another half of another different material. But in uh, films, it's more common to have different layers, which may be packed with uh, different orientations, or you have substrate and there are different nano thin, nano thin films coated on top, which can be like different materials. You can have uh, silicon, and then you'll have a thin layer of nickel, and then on top of that, you have a thin layer of gold. Okay, so okay, these thin films are in a 2D nanoparticles. Okay. Yeah, these can be deposited on the substrate, integrated into surrounding matrix, and yeah, can be metallic and polymeric. 3D nanomaterials are a little different. So 3D nanomaterials or bulk nanomaterials, they are not confined to the nanoscale in any dimension. The material, those are characterized by having the three dimensions uh, above 100 nanometers. Okay, but so why are we calling it nanomaterials? So usually they form composites of, uh, they usually form composites with other type of nanomaterials. So here you have grains which are in nanometer scale. And you combine those grains together to get a bulk which is greater than 100 nanometers. But since the grains are smaller than 100 nanometers, you still call it nanomaterial. Or you can have nano precipitates, right? Then precipitates or nanoadditives, particles in nanometer size scale, nanometer scale, providing strength of any other property you want. So again, so three-dimensional or bulk nanomaterials, they are mostly just composites. Material possess nanocrystalline structure or involve presence of features in nanoscale. In terms of nanocrystalline structure, bulk nanomaterial can be composed of multiple arrangement of nanocrystal nanosized crystals, or typically in different orientation. Yeah, this if you see different grains, they would be oriented in different directions, and yeah, bulk is composed of bulk grains. With respect to presence of these feature at nanometer, 3D nanomaterial can contain dispersions of nanoparticles, bills of nanowires, or nanotubes, as well as multi nanolayers. There are some examples of 2D, 3D nanocrystals. There you have substrate, and on top of it, you have a thin film. If the thin film thickness is less than 100 nanometer, you call it nanocrystallite, nano uh, film. If it's micron range, you call it crystalline. You can have different layers, different layers. Each layer is again in, and then less than 100 nanometer, you can call it a nanomaterial. And if you stack multiple of these nano layers, nanofilms, thin films, you get a composite of them, which would give you a 3D nanomaterial. There are some examples of matrix reinforced layer nanocomposites. Here you have bulk, which has small nanoparticles inside. Okay, uh, so this is a bulk nanomaterial with nanoparticles embedded inside a matrix. Or you can have a matrix which is reinforced with nanowires or nanotubes. We have small tubes of nanowires inside your bulk. The bulk nanomaterial with uh, nano 2D nanotube, oh, sorry, 1D nanotubes or nano rods embedded inside a matrix. Matrix. Or we went from 0D additive, 1D, now 2D. In 2D, you have different layers. So the layers, and if you combine them, join them together, and then you get a bulk material composed of different layers of 2D nanomaterials. Finally, you can also have sandwiches. So in middle, you have a thick bulk material. On top and bottom, you have two nano thin films or nanofilms, films in nanometer scale. So again, you get a bulk nano material. It has nanofilms on the either side. So yeah, these materials are found when two or more materials with very distinct properties that act synergistically to provide properties that cannot be achieved by each single material alone. The matrix of the nanocomposite, which can be polymeric, metallic, or ceramic, has dimension larger than scale, whereas reinforcing phase is commonly. Okay. Uh, These are 3D nanomaterials. So where you have gold ruby glass. In this case, you have this is your matrix. Here you can obviously see there are perfectly ordered and zero-dimensional nanocomposites just because they are nanoparticles. Okay. They can be in this one. You have uniform particles arranged uh, in a perfect order. It's not necessary they follow. They can be uniform sized, but uh, they can be arranged randomly. They can be non-uniform sized and arranged randomly. Like in this case, they have different sizes, again arranged differently. There you have some composite fiber consisting of polymer bond in nanocarbon nanotubes. Dimensionality and class of nanomaterials. The first class mm, is your discrete nano objects. In discrete nano objects, you can either have then you have different dimensionality. So in discrete nano objects, which are 0D, you get nanoparticles, which can, like example, as smoke or diesel fumes. So particles are again nano meter scale. Distinct particles, but in they are one dimensional, so you have carbon nanotubes. Then you have distinct nano objects which are two dimensional, which gives you a nanofilms or foils. Okay. The next category is surface nano featured material. Okay. So here with class 2 surface nanomaterial with 0D nano uh, scale material, you have example of a nanocrystalline film. The film itself is very thin. There is a nanometers, and it's made up of individual grains which are less than themselves are again fall within this 100 nanometer range. Even though the joint film is more than 100 nanometers, since the grain are just basically 0D nanomaterial, you go to class 2 with 0D nanoscale material. If you again see surface nano featured with 1D nanomaterial, you have nano interconnects like nanomaterials. So you have film, but all these rods are connected to each other in this mesh-like structure. So it is this is very dense, like almost. If you join them together, it's similar to like this. So you have film again. This thickness, if it's very small, like 100 nanometer, and you get a thin film made up of 1D nanomaterials. Finally, thin film with 2D nanomaterial is just a film, nanosurface layers. Satisfy all these conditions. In class 3, you have bulk nanomaterial using 0D nanoparticles. So these are like examples we told before. Nanocrystalline materials or nanoparticle composites. Class 3 bulk nanomaterial with 0D is the like the example we saw. 2 slides back. Matrix reinforced with nanoparticles. Right. This we've already seen on 3 examples. So the nanocomposite with composite with nanoparticles. Here you have bulk with 1D nano rods. So a nanotube reinforced composite. Second one. Finally, you get bulk structure using 2D nano materials, like nano sheets. Maybe. Yeah. So there you can have laminates of standard uh, type structures. Okay, self-assessment question. The second lecture. So how 1D, 2D, and 3D nanomaterials show different properties in the characteristics. So if you go down to from 3D to 2D to 1D, your quantum confinement effect starts playing a role, like your band structure changes, your like, band gap changes. So that as you go down the length scale is uh, playing a big role. The aspect ratio changes. 3D, 0D have really very large aspect ratios. Thickness is very small compared to the length. Changes from as you change from 1D to 2D, 3D. Conductivity, yeah, some materials are really conductive. Uh, for example, graphite. Graphite is an example of 3D nanomaterial. However, we go down to 2D, you get graphene. Graphite, graphene. You see, graphene is much more conductive compared to graphite. So, can have different layer structures. Surface area changes as you go from 3D to 2D to 1D. Morphologies, like 2D, you can have plates of different shapes. Where 1D, structure you find in 1D, like rod or tube, that won't form in 2D nanomaterials. What happens to the surface when it becomes really small? So if the particle becomes really small, a lot more atoms sit on the surface. So more atoms are exposed to the environment, and those atoms sitting on the surface have unfulfilled vacancy. So they're really reactive. And yeah, depths are particularly high energy surface suitable for catalysts. So you go down to nanometer scale, you find is the shape of particle is not really um, continuous, but in steps. So each step would be a atomic layer thick. And the next, there's another layer of atoms. Yeah, these steps, sites, they're really high in energy and suitable for catalyst. So how does your surface to volume relationship changes depending on different metric shapes? So if you remember surface area, okay, area divided by volume in with cube. So cube we have six faces. One, two, three, four, and fifth one in the back, and the sixth one in the front. Third is the bottom one. Okay. We have six faces. Area of each face is length into breadth. L into L. L square is the area, and you have six such faces, so 6L square. So I have 6L square divided by volume. So that's just L cross L, length cross breadth cross height. Okay. All three are L, and L cubed. That's two. So you get 6 over L. Similarly for sphere, if you remember the surface area, that's 4 pi r square. And the volume is 4 by 3 pi r square. Pi cubed. Mm, Is it 2 by 3? Volume of a sphere. Mm, 4 by 3. I think this is incorrect. Surface area for a sphere would be 4 pi r square. Volume would be 4 by 3 pi r cubed. Pi pi cancel. R cube r. 4 4 cancels. So 3 by r. The answer. Yeah, 3 by. Oh, yeah, r. R and D. This is correct actually. Mm. I was talking about R, and this is D. So R is just D by 2. The radius is half the diameter. Yeah, you get this. This is substitute R. So we're talking about the largest the dimension you see. So diameter. So for a wire where your height is much greater than the diameter. Okay, so let's calculate the surface area volume ratio for L. We'll do cylinder first. If you have a cylinder, this is the D, and here H, which is also equals to D. So its surface area would be uh, the curved surface area is 2 pi mm, r, 2 pi r, which is 2 pi r into the length h, or you can write as d by 2, 2 pi d h by 2, or by dh, and yours end surface area is pi r square, pi r square, or pi d square over 4. The total surface area S total is equals to 2 times pi d square over 4 plus pi d h. Since h and d are equal, you get pi d square over 2 plus uh, pi d square. You get 3 pi d square over 2. This is just the surface area. Volume is just pi r square over, yeah, pi r square into h. Hmm. Volume is also pi r square into h, which is pi t square over 4. If you take the ratio of these two, you should get this value. Okay. In case of wire where h is much greater than d, you ignore these two values and just calculate the surface area to volume ratio using the curved surface area and their volume. The curved surface area is just 2 pi, the circumference into the length, 2 pi d, 2 pi r into 2 pi r, d by 2 into h. Try this at once at a home, and if you have a problem, you can message me, or in the next class you can raise it out. Okay. Some practice questions. Which of these historical works contain nanotechnology? So you already saw the like Argus cup, which has nano gold particles, giving it different color under different illumination. Yeah, stainless steel, the stained glass windows in the churches. Again, we saw that they have different nano particles and nanoparticles of different metals, which give them different colors. And yeah, Damascus steel sword, they have grain size, which are again in nanoscale. Or they have like layers of nanomaterial, I think. Special about Damascus steel. Three of them are correct. What is a buckyball? Buckyball, if you remember in the last class we saw. Uh, it's a football shaped. Difficult to draw, but yeah, football shaped uh, nanoparticle made up of just carbon atoms. So the typical one is C60. The buckyball is referred to just the C61. You don't do it for the largest C70, C80. close the notebook even. Mm, Great last thing. Mm. Which one of these statement is not true? Gold at nanoscale is red. True. I think in the last class we saw. This is again true. Metals at nanoscale are very combustible since they, most of the atoms are sitting on the surface, ready to oxidize. Any oxidation happens, it will raise the temperature, causing more oxidation. You have another reaction, causing explosion. Silicon at nanoscale is an insulator. This is again true. Here, if you know the silicon's band gap 1.2, we go down to nanometer scale, the band gap increases this and is, yeah, the band gap increases and you starts behaving more like an insulator than a silicon. Next, we have copper. The copper doesn't become transparent if you go down to nanoscale. And gold we already saw. So we have this. Which of these consumer products is already being made using nanotechnology? I think it's sunscreen lotion. Not sure what does it do. Yeah, these are titanium oxide nanoparticles which absorb the UV light. They absorb the UV light and they release it in infrared region. So it doesn't harm your skin. Plasmonics, again, it's just a definition. Plasmon is a collective oscillation of uh, surface plasmons in the on a metal nanoparticle. If you're a metal nano uh, particle, you know, in metals there are free electrons. The electrons would be freely sitting on the surface, and if a electromagnetic wave passes through, these electrons start themselves oscillating in response to this electromagnetic wave. So this uh, wave of charged particles on the surface is plasmon. So let's eliminate. This is incorrect. This is very what is this field of nanophotonics? They're not related. So you only see this plasmon effect when your particle size is really small. a material with one dimension in nanometer and other two in other two dimension which are large. So, for example, sheet, right? Thickness is in nanometer and length and the breadth is bigger than 100 nanometer. So quantum, if you eliminate not micromaterial, not quantum wire, wire is just one dimension is greater than nano outside the nanoscale. A quantum dot all three are in nanoscale. You want a sheet. So quantum well is just two materials which are bonded with a very thin layer of uh, different material. This thickness is in nanometer scale, but these two dimension are again much greater than nanometer. Quantum well. The first talk of nanotechnology. I think this was covered in the lecture. Richard Feynman was the one first referred to talked about nanotechnology. You go take the particle size to nanometer scale. Melting point of particles in nanoform usually decreases, and we'll go over the exact reason right in later lectures. Yeah, just remember as the size decreases, your melting point also decreases. 1 micrometer, the micrometer is 10 to the power minus 6. Or this is millimeter. Millimeter is 10 to the power 3 meters. Micrometer, 6 meters. Then you have your nanometer, which is 10 to the power. Micrometer is 1,000 times bigger than a nanometer. 1,000 times bigger. A material is said to be nanomaterial if at least one of the dimension is has to be in nanometer. Angstrom. The nanometer is 10 to the power minus 9 meters. We just saw that. One angstrom is 10 to the power minus 10. If you just divide these two, 1 divided by angstrom, 10, 10, 1 nanometer is if you break a bulk object into large number of small pieces, keeping the volume constant, then the number of atoms attached to the surface will increase. So if you have a cube, put it into smaller cubes. Your volume is being conserved, but the surface area is increasing. It is as of atoms attached to a surface. All three dimensions of material are in nanoscale. So, in a sphere, all dimensions are less than 1 nanometer, so maybe 10 nanometer. You get a quantum dot. PiO2 is a nanoparticle used marking roadsides. I think the correct answer is it does act as a photocatalyst. It's visible from long distance, and the presence of light it oxidizes the lead particle and pollutants to maintain its white color. Just give me a second. Okay, nanomaterial are unique in sense that again, since most of the atoms are sitting on the surface, they are high energy state material. They are actually very reactive. They have satisfied bond on the surface. So A and C would be correct. Millions of dash. The gecko feet is made of millions of keratin hair, which provides a strong adhesive force. System to stick to any molds. Highest packing fraction comes in again. You remember a bit of crystallography. Okay, yeah. Yeah, hexagonal structure, you remember, is the most space efficient. There's no space in between and gives you maximum packing fraction efficiency. Interfacial energy will be small if the matrix and the precipitate has uh, same structure actually. So if they have same structure, then there's an adjacent atom sitting. There's an atom sitting right next to the atom. If there's a mismatch between this, Like there's no atom here. It's just the spacing is larger. The example like larger bond lengths. This one is there's a bond, but this one is missing a bond. Uh, so if the structure matches perfectly, there's one-to-one mapping. If it doesn't, this one has a bond, this one has a bond, but this one doesn't have a bond. So uh, the interfacial energy will be larger. Fill in the blanks. Higher interfacial strength and lower interfacial tension of the precipitator matrix phase two. So in a matrix and a precipitate material, what you have is a matrix, and then there are precipitates. So they are odd maybe, or a particle. Let's go with the particle. Particle sitting inside a matrix. Okay. If the bonding at the interface is strong, what will happen if you try to break it? The energy would be absorbed. And if the crack needs to pass through, it will pass through the nanoparticle. And if this is much more tougher, harder, usually this is harder than the matrix, it will require more energy to break. However, if the interface is weak, what will happen is crack would go around the nanoparticle. Yeah, their overall material strength is higher in this case, strength, and more tougher. Ah, I'll end the session here. I'll a few more practice questions, like 10 more problems. I'll take them up in next session along with the first and second assignment. Yeah, just remember, uh, Wednesday is the deadline for the both assignments, so be sure to complete them. I'll go over these questions in the next session. That's just 10 questions. Thank you so much for attending. And if you have any doubt, you can message me. Thank you. Okay, so nanomaterials exhibit interesting properties because of large number of atoms setting. So again, um, nanomaterials have large surface to volume ratio, so as a percentage surface. Yeah, yes. That's what it gives their interesting properties. Since these are surface atom will have unfrequent valencies, they wide sites for reactions for take place. Yeah. Surface plasma excitation in nanoparticles. Okay, so surface plasma excitation occurs when you have metallic particles which have free electrons sitting on top. When electromagnetic wave passes close to this nanoparticle, and these free electrons oscillate inside on the surface of this nanoparticle. This collective oscillation of the free electron is called plasmon excitation, and it happens usually when it happens when the wavelength of the light and the particle size are comparable. So do the detect. It's not necessarily true. For example, wavelength of visible light is around 400 to 700 nanometers. So, for example, gold nanoparticles show surface plasma resonance at around 520 nanometers. These are fairly large particles. Yeah, within the environment. And they will, as per strictly as per the definition of 100 nanometer. Yeah. Okay. Mm, Bulk nanomaterials are basically, they do fall under category of nanoparticle. This is false. They are three-dimensional nanomaterial. It's true. Yeah, we're calling them bulk nanomaterials, so they're 3D. And nanoparticle generated the matrix because so there can be other things too, but this is possible. If there was only single option to tick, B would be the most correct, since there are multiple options. B and C both are correct. Classification parameter of nanomaterials is done based on. So you have 0D, 1D, 2D, and 3D. Classification is done based on how many dimension is bigger than the. So for 0D, you have zero dimensions less than 100 nanometers. It's a dot. Out of dot. So for 1D, only the length is sorry, it should be zero dimension or more than 0D, all dimensions are less than zero dimensions are more than. So for 0D, it's one dot. For 1D, one dimension is more than it's a rod. For 2D, it's a sheet. two dimensions are bigger than and so on. So how many dimensions are more than 100 nanometers? What can be the structure of nanomaterials? And we have discussed this before. They can be polycrystalline, small, and amorphous. There have been work recently done for glass nanoparticles, amorphous in nature. Needle-shaped nanoparticle are example of needle-shaped. Again, we have one dimension which is bigger than another node, um, greater than 100 nanometers. Other two are less. So this is 1D. This is an example of a one-dimensional nanomaterial. A thin film on the substrate is said to be nanomaterial. We have substrate, so this is a substrate. On top of this, you have on top of this, you deposit a film. This is a film. This is less than 100 nanometers, 10 nanometers, nanometers. Okay, so this is said to be a nanomaterial if the thickness of the film is a nanoscale irrespective of the. Yep, this is true. The thickness should be nanometer. All three dimensions, all three dimensions are beyond nanometer range. This is false. Component, all three dimensions are beyond nanometer range, but grain size of the film is in nanometer range. So this is also if this film is big enough, but individual grains are in nanometer scale, we still would call it a nanomaterial. Quantum dots, quantum dots, very small particles where X, Y, Z, all dimensions, size are less than the nanometer. Example of zero D material, zero dimensional material. Okay. What happens to the thickness of a surface layer? What happens? The thickness of the surface layer of a nanomaterial increases. This is your nanomaterial. You're increasing the thickness of this layer. More number of particles will be attached to the surface. Surface to volume ratio will increase. The larger particle size approximately, surface effects will be less significant on the field. So, so, if you're increasing the thickness, more particle will be attached to the surface. This is true. This is the thickness layer is uh, thicker. There are more particles to consider on the surface. This is true. Surface to volume ratio will increase. Since your surface, more of the surface, your surface, the bulk volume is reducing and your surface is increasing, so surface to volume ratio is increasing. Right. Surface to volume ratio decrease and the effect due to surface will diminish if the particle size is relatively big. Use of all of these effects will be effect. What if a particle size is less than gravity? This unusual bending starts to play in the world. Particles are less than 5 meters. Fractional surface atom sitting on the surface will be significantly large. This is also true. Yeah, the particle is made up of maybe hundreds of atoms. Correct. Fractional surface will diminish. Correct. Will actually decrease. Surface effects are really important now. So the atoms are sitting on the surface. Then in this. Hmm, yeah, okay. I think I can end the session here and add it to the remaining session. This was a recording session because I started the previous session too late and time left after 8 p.m. So yeah, as always, you can message me on the address png dot Nara and UKR D content. If you're in doubt, please feel free to message me. I'll try to answer them. And you can also post your queries on the discussion section in your NPTEL course page. Okay. Thank you.